Hello, grade 12s. Mr. K here in the Corona bunker. This is the first thing we're going to learn in Anatomy and Physiology 12. This is the beginning. What we're going to be learning about is going to permeate the rest of the course. Everything here you will run into again and again as we go through the course. So albeit this stuff may be not the most interesting part of the course, although, you know, it's somewhat interesting, it is very important. And what I'm talking about, what we're going to be talking about in this unit is basically chemistry and biochemistry. This course is Anatomy and Physiology. It's about you. And you are chemistry. You run on chemistry, on biochemistry, biological chemistry. So let's talk a little bit about chemistry. So the focus here in this first section is the characteristics of chemical systems. So it's just some general overview of chemistry and of water, which is very important to biology, water. What does this say? The survival guide, how does it go? It's you will die 3 days without water, 3 weeks without food, and 3 months without shelter. That is if you're stranded out. So water, you only have 3 days. Water is very important. So we're going to talk about water and why water is so important. And what makes water important is its chemistry. I think those are averages. Maybe some of you could survive 4 days without water, right? Okay, so let's start talking. Let's talk about what is chemistry. What do we talk about when we talk about chemistry? You know, we're talking about atoms, and we're talking about atoms interacting with each other. So we're talking about bonds between atoms. How do atoms bond together? That's chemistry. And there are 3 main types of bonds. There are covalent bonds, ionic bonds, and hydrogen bonds. And then there's a subset of covalent bonds called polar covalent bonds. In this course in biochemistry, we're mainly going to be dealing with covalent bonds, polar covalent bonds, and hydrogen bonds. Those are going to be important. Ionic bonds, not so much, but let's just go over them anyways. There's still going to be some ionic bonds. We need to understand what those are. So the first type of bond is covalent bonds. What happens in a covalent bond? So when we talk about chemistry, you know, we talk about atoms. Atoms have a nucleus with electrons orbiting around. You should already know this. And in chemistry, when bonds form, when you have chemistry, it's the electrons that are interacting. It's not the nucleus. Nucleus is nuclear fission or fusion. When we do that, we can do that, but not in biology. So, covalent bonds are the strongest type of bonds, because what happens in a covalent bond is there's 2 nonmetals. So when you look at the periodic table of elements, if I had a periodic table element here in the bunker, I don't. On this side of the periodic table are all the non-metals. So you're talking carbon, nitrogen, hydrogen. Well, hydrogen's a metal. We've got carbon, nitrogen, hydrogen's special. Oxygen, those are all the non-metals, and they can form covalent bonds. And what happens in covalent bonds, why they're so strong, is because they share their electrons. So basically, instead of the electron just orbiting around one nucleus, it starts to orbit around 2. If we look here, 2 or more. So if we look here on, there's some notes here. Let me just adjust it. There we go. So if we look, we've got, this is just a diagram of carbon dioxide. And you got carbon with 2 oxygens, and what you have to imagine is there it's sharing those electrons. So those are the covalent bonds. And basically you imagine that the electrons are doing a sort of like the clouds of electrons have merged, and they're sharing those electrons. So those are covalent bonds. sharing electrons between two nonmetals, the strongest kind of bonds. Covalent bonds are the strongest. Ionic bonds, what happens in ionic bonds is atoms want to have a special number on their outer shell of electrons, 8. And sometimes it doesn't work out. You know, when you look at certain atoms, they don't have 8. Chlorine, for example, I think chlorine has 7 electrons on the outside. And so what they want to do is either they want to take on an electron to get them closer to 8, or take on 2 electrons to get them to 8 in their outer shell, or if they're a metal, they want to give electrons away. So an ionic bond is between a metal and a non-metal. So for example, sodium chloride, soap, not soap, salt. What happens is look here. What happens is they form ions. And so they want to get to a stable outer shell. So here, sodium, if it gives up one of its electrons, if it just loses an electron, it will have then 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer shell. So it becomes an ion. An ion, what that means, it just doesn't have an equal number of electrons and protons. Because remember, in the nucleus is the same number of protons when it's an atom as there are electrons to balance it out. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. That means there are 11 protons in the nucleus. So now it's lost a electron. So now, because there are 11 protons and only 10 electrons, it's got a positive charge of 1. So basically that's what means an ion. Ion is just an atom with a charge. And chlorine here, it's got 1, 2, 3, 4, 5, 6, 7 electrons in its outer shell. So it wants to gain an electron. So if sodium wants to lose one, chlorine wants to gain one, chlorine gained one. But now it's got too many electrons in its overall, because remember here it'll have the same number of protons. So there's one less proton here, so it's got a negative charge of 1. Long story short, it's negatively charged, positively charged. Opposite charges attract each other, so they just get closer together. But they're not sharing electrons, they're just close together. It's a very chaste relationship. They're not sharing fluids. This is more of like a grade 8 dance or a grade 7 dance. Whereas the covalent bond is a disgusting fluid sharing grade 12 dance. So as a result, ionic bonds are weaker. But that's what happens in an ionic bond, is you form these ions and they come together. You already know this from some chemistry class from grade 10. This is all review, but we need to go over it. Sodium chloride, important in biology. Next, let's talk about, so let's go back to covalent bonds and talk about covalent bonds, because there's something called polar covalent bonds. And polar covalent bonds are still covalent bonds, just like the ones that we talked about where electrons are being shared, except there's a little bit of ionic bond kind of bondingness going on, because the sharing isn't equal. So what that means is that when the atoms come together and they share the electrons do that loop around all the atoms, they spend more time around certain atoms than they do around others. And so now as a result, electrons are negatively charged. These atoms that the electrons are spending more time on become negatively charged, and the ones that don't get as many electrons become a little bit positively charged. And so that's a polar covalent bond. Let's look at an example of one. The best example is we've got an oxygen and 2 hydrogens, H2O. And so as you can see, the electrons, because oxygen is a fairly large positively charged nucleus with a lot of protons, the electrons want to spend more time there than they do around hydrogen. Hydrogen has just one proton in its nucleus, so the electrons don't want to spend here. They're not attracted to those hydrogens. So they spend more time around the oxygen than they do around the hydrogen. So the focus has gone caca cuckoo here. Let's see if I can lock it down for you. There you go. And so because the electrons spend more time around the oxygen, don't focus on my finger, you evil thing, the oxygen becomes negatively charged and the hydrogens become positively charged because the electrons are spending less time there. So as a result, the entire molecule now has a dipole. It's got a basically one end of it, because the electrons spend more time on one end than they do on the other end, is negatively charged, and the other end is positively charged. And this is a very good property of water, because so if you imagine another water molecule here is going to be attracted, the positive end is going to be attracted to the negative end of the adjacent molecule, and as a result, water likes to stick together. It forms these weak bonds together, kind of like ionic bonds, except they're between molecules. They're not between ions, they're between molecules, and these charges aren't as strong as these ionic atom charges. So what happens is these bonds that form between these molecules that have this dipole, that have one end that's negative and one end that's positive, is called a hydrogen bond. So basically what happens in water is that these hydrogen atoms, which are now slightly positive because they're losing those electrons to the oxygen atom, even though this isn't an ionic bond, it's a covalent bond, they're still sharing them. Those electrons will come around and loop here. They just spend more time here. So these hydrogens will be attracted to an adjacent oxygen. I know, it's crazy. And so as a result, these hydrogen bonds form in water molecules. So here you go, look, here's a water molecule, there's the hydrogens, and see, they're all attracted to each other. They're not forming something new, they're just sticking together. And well, this leads to a whole bunch of amazing properties of water. So these dipole moments cause these hydrogen bonds, is basically where a negative end of a molecule is attracted to a positive end of an adjacent molecule. And these don't have to be between water, they can be between other things. So water has these unique properties as a result. One of these properties is called cohesion. So notice the water molecules are attracted to each other because they're attracted to each other. They've got a hydrogen bond here. And hydrogen bonds are weak. They're not a strong bond. But added all together, there's so many water molecules, there's so many hydrogen bonds, it starts to become a strong thing. So if I drank my water, but there's a little bit of water here. So you can see water, I don't know if you guys can see that, the focus will be all crazy, but you know that water sticks together. We know that water sticks together. Look, if I pour some water onto my hand, okay, I don't know if the focus will work or whatever, but look, there's a water drop. I don't know if you can see that water drop on my hand, and it will stick to the water here. I can pull the water together. And this cohesion, this stickiness of water is very important. It's important to biology, and it's essential. It's essential. So if you think about plants, plants need water. They need water to carry out photosynthesis and whatnot. And so the photosynthetic structures of plants, leaves, are way up high because they're competing with their neighbor plants. So they've evolved to be higher and taller and taller and taller so that they could get more sunlight. But where's the water? The water comes in the roots. And they need water to carry out photosynthesis and to do other functions, to do something called cellular respiration. We're going to be talking about cellular respiration a lot. And cellular respiration is the process of breaking down food, breaking down sugar, and turning it into energy. It's metabolism. It's what all living organisms do. They metabolize sugars to create heat so that they can exist. That's what's happening. So plants do this. And plants use photosynthesis to make their own sugar, which then they will metabolize. And they need water all to do that. So how does the water get up to the leaves? Plants don't have a pump. They don't have muscles. They don't have something that squeezes and pumps the water up. How water crawls up a tree is amazing, because how it crawls up is the water sticking to itself, is this idea of cohesion. So in the leaves are little doors called stoma, and they open and the water evaporates. And as one water molecule is evaporating, it's getting enough energy from the sun, from the heat, to lift itself out, to leave. It still has enough cohesion to hang on, to have hydrogen bond to another water molecule, and so it pulls that water molecule. As that one water molecule leaves, it grabs another water molecule, which then grabs another one, which then grabs another one, which then grabs another one. And that grabbing, that cohesion goes all the way down the tree like a chain, each molecule grabbing the next subsequent molecule, and pulls the water out of the ground and through the tree. So if there were no hydrogen bonds, if water didn't have hydrogen bonding, it wouldn't stick to itself and trees wouldn't be able to exist. They wouldn't be able to have water running through them. So cohesion, important. The other thing, it allows water to travel up in tubes, and also that's important to us. We have, all kinds of whole circulatory system. Most of our blood, or 50% of our blood, it's like 50%. We'll go over it in the circulatory unit. I'll read it before I give you the notes. Is plasma, and plasma is basically water. So we have a lot of water, and it also sticks, it pumps through our veins. We do have a pump, we have a heart, but also, when it's traveling through the lymphatic system and through our veins, the heart isn't actually really pumping our blood at that point. It is actually moving, and part of that is thanks to cohesion. The other thing that hydrogen bonding allows is, because water has these charges, and it has these hydrogen bonds. Basically, when you heat water up, you add heat to it. So heat is kinetic energy, and or even radiation from the sun. When you're putting energy into water, basically what happens is the water molecules start to vibrate faster, but that vibration is dampened by the fact that it's basically chained together to other water molecules. It doesn't, the water molecules don't just start to vibrate because they have all these hydrogen bonds kind of holding them together. So as a result, water is a good absorber of heat. It mediates heat. It hangs on to heat. And it also resists absorbing, not absorbing, because it absorbs heat well, it resists changing phase. So basically it resists boiling away. That's why it takes, water's liquid for a very long time, up to 100 degrees centigrade, before it starts to boil away. Because what happens is the water starts to vibrate, one of those hydrogen bonds breaks. That breaking of the hydrogen bond actually takes that kinetic energy and absorbs that kinetic energy, and then another hydrogen bond forms immediately. Water can have up to 4 hydrogen bonds, so it can have up to 4 water molecules. One water molecule can have up to 4 water molecules attached to it. So as you put more energy in, bonds are breaking and new ones are forming, and this is absorbing that heat energy. So water is constantly absorbing that heat energy until finally there is so much energy that those hydrogen bonds can't keep up, and the water molecules pop off and they start to boil away. But this is important, this maintaining the ability to maintain having high heat capacity to absorb heat, because we use it to not boil away. Right? Our bodies are water, a lot of water, because we're able to maintain homeostasis this way. We're able to maintain a steady temperature no matter what's happening, whether there's a heat wave, a cold snap. Water has this high heat capacity, can hang on to a steady state of temperature. What else? What is another property of water thanks to this hydrogen bonding? Water, because it has this dipole, positive end and a negative end, it actually becomes a really good solvent for ionic compounds. So salt, for example, those charges of water, there's all these now charges, negative and positive charges. Remember, ionic compounds are a positively charged atom and a negatively charged atom. They're sort of just getting close together. They've given away an electron. One has taken an electron from the metal, has given an electron to the non-metal, and so, but they're stuck together because they have a positive charge and a negative charge. But all these water molecules are now everywhere with their little charges, with their little dipoles, their polar covalent bonds, and their little hydrogen bonds and stuff, and they start to rip at this ionic bond, and eventually they get in between and break it. And so as a result, salt dissolves in water. Ions can dissolve in water. Ions can move through water. And we use those ions in many processes. Our nervous system works on pumping calcium across membranes. A lot of systems work on ions, on salts working in our body. And that is another function, another result of those hydrogen bonds in water. And finally, what else can water do? So water is, we got high heat capacity. It sticks to itself. That helps liquids flow. Is a good solvent for ionic compounds. And is a lubricant. Water is a lubricant. It's slippery because it kind of sticks to itself. It has a kind of viscosity. So our joints are lubricated by water. We lubricate our food with water. We have these salivary glands here. We excrete water into our mouth so that when we eat food, we saturate it with water and it can slide down into our stomach easier. And finally, the last property of water is has a unique property. You may have experienced it, is when water freezes. Normally when something freezes, its density increases. Its density goes up. The molecules, as things get colder, the molecules stop moving, they slow down, and they just vibrate slower. They get closer together. So as a compound goes from liquid to solid, the molecules get closer together. And therefore its density is greater. There's more mass per little volume of space because the things have come closer together. And so if you put liquid, if you put a cooler, even a cooler liquid in a hotter liquid of the same, like air, let's say for example, okay, so a gas, as air cools, it doesn't even become a solid, but as air cools, the molecules get closer together, the density increases, the cooler air will sink and hotter air will rise. The same thing for water. As water heats up, hot water rises and cold water sinks. But as water turns to a solid, it does this strange thing because of the structure of water. Instead of it getting all closer together, water actually forms these lattices. It goes when it turns into a solid, and it actually becomes less dense than when it was a liquid. So if you imagine water is getting colder, let's say it's freezing, it's getting colder, as it's a liquid, it's getting denser and denser, but then as it turns into a solid, it turns less dense and the ice floats to the top. And this is important for life and for survival, because if you imagine lakes that freeze over in wintertime, they get a nice protective coating on top of the lake of solid ice that actually insulates the liquid underneath, so that fish and organisms in the water can exist. They can actually, the heat kind of stays in, they can hibernate, they can whatever, but the water stays liquid. It's harder for it to freeze throughout. Okay, so we've talked about that. What else is there in this section? Let me just flip through here. So we've talked about, so these are properties of water. So this is why water is important to life. It lubricates. We talked about hydrogen bonds. We're going to be talking about hydrogen bonds again when we talk about proteins. We talked about polar covalent bonds. Just moving through this A1 unit. There's a lot of stuff here. Specific heat capacity, lubricant, acids, bases, pH, and buffers. So the other thing that's important, another basics of chemistry, is this idea of acids and bases. So the fundamental difference between acids and bases, some examples of acids, I mean, you've all experienced acids, lemon juice is an acid. What's a base? There's somewhere in here, here we go. Drain cleaner is very basic, but bleach is very basic. Ammonia is very basic. Your stomach acids is very acidic. Lemons are acidic. Milk is acidic. Blood is a little bit basic. Water is neutral. So what does that mean to be acidic or basic? Well, what we have to understand, and this is for this course, what acidic means is acidic compounds, what they do is they release excess hydrogen ions, basically hydrogen nucleuses, into solution. So when they're in a solution, that solution will all of a sudden have more hydrogen nucleuses, H+ ions, which brings up an interesting thing that I saw somewhere on the internet, is when you taste lemons and you taste the acid has a certain flavor. You have specific taste buds on your tongue that can taste acid. Basically what you're tasting is those excess hydrogen ions. You're tasting the protons. You're tasting hydrogen nucleuses. That's what a proton tastes like. You can't see a proton, but we can actually taste them, which is kind of strange. So acidic solutions release, I'm just checking the time here. Oh, this is a very long video. The subsequent ones won't be this long, at least for this unit. There'll be some long videos, oh, trust me. But it's hard as your first video, none of you will probably watch this, but it'll all be on the test. So acidic compounds release excess hydrogen ions. Basic compounds release excess hydroxide ions, which is OH, which is basically OH. So OH minus, there'll be a lot more OH minus. That will be a basic compound. Water is neutral because water is H2O. So when it dissociates, it releases H and then an equal number of OH. So it's neutral because there's no excess H and there's no excess OH. The way the pH scale works, it's a reverse logarithmic. We don't have to worry about the detail of it. But basically 7 is neutral, that's water. A pH of 7 is neutral. We're gonna be talking about pH, well, when we get to respiration and circulatory system for sure. We're gonna be talking about pH when we get to the digestive system. We're gonna be talking a little bit about pH when we get to the urinary system. So this is why, all of these things, we'll be talking about all the things that I've been talking about. This is a very important unit. So water is neutral, 7. So everything past 7, 7.1 is basic to all the way to 14. It ends at sort of at 14. That's the most alkaline, the most basic you can get. And then a pH of 0 as you go down is things become more acidic. So at 7 and then moving up, or I guess for you guys moving up from 7 to 8, 9, 10. There'd be an excess of more and more and more hydroxide ions, OH ions. Moving down the pH scale past 7, now you're getting to an excess of hydrogen ions. At 7, that's water, you have an equal amounts of hydrogen and hydroxide ions. That's basically what pH means and how the pH scale works. And the final thing to talk about in this review of chemistry is buffers. Buffers are very important. What buffers do is they maintain a pH range by absorbing excess hydrogen ions or excess hydroxide ions or releasing hydrogen ions or releasing hydroxide ions. So if your blood becomes too acidic, there's too many hydrogen ions, a substance called bicarbonate, which is a very weak base, will take up those excess hydrogen ions to a certain degree. If too much hydrogen, a buffer can only go so far. So if there's too much hydrogen ions, there's not enough bicarbonate to endlessly absorb those hydrogen ions. So buffers, important thing to know is they're a weak base or a weak acid, and they will either absorb or release hydroxide or hydrogen ions to maintain a stable pH. And that's the last thing of this chemistry review. So what are we talking about in this chemistry review? We've talked about so much. Things to remember: the bonds. Ionic bonds are the strongest. Covalent ionic bonds, ionic bonds are the strong. That's wrong. What to remember from this unit: covalent bonds are the strongest. Polar covalent bonds, a special type of covalent bond where the electrons are not equally shared in the covalent bonding, so the molecule has a polar moment, which means the molecule, one end will be positive, one end will be negative, which is what happens to water. Ionic bonds are weaker. Basically, ionic bonds are not electron sharing. They're ions giving away and taking up electrons, therefore becoming charged and therefore associating, getting close together because they have a charge. Hydrogen bonds are where molecules that have a region of either negative or positive charge are attracted to the opposite charge of adjacent molecules. So water has lots of hydrogen bonding, but water is not the only thing that does hydrogen bonding. Other molecules can have hydrogen bonding because they'll have regions that are positively charged or negatively charged. We're going to talk about that a lot in proteins when we talk about proteins and enzymes. As we talked about bonds, we talked about water, all the properties of water. So water has cohesion, high heat capacity, it's a good solvent, it's a good lubricant. There's 5 things. What's the 5th thing? Specific, ice. It turns into ice. The ice floats. This is not so much. But what else? Water is transparent. That's also actually an important property. You'll read that in the notes. We talked about acids. An acid means solution has excess hydrogen ions. A base has excess hydroxide ions. Neutral water is neutral because it dissociates to equal amounts of hydroxide and hydrogen ions. pH, a low pH, so a pH of 2 is acidic. A high pH, pH of 10 is basic. 0 is the most acidic you can get. Basic is the most basic you can get is 14. I don't know if there's higher. Well, I wonder. You'd have to look that up. It's an inverse logarithmic, so there's probably and buffers maintain a steady pH by their absorbing hydroxide ions or releasing absorbing hydroxide ions or absorbing hydrogen ions or releasing. So basically, not absorbing; they're bonding with the hydrogen ions or bonding with the hydroxide ions or unbonding, breaking the bond of the hydroxide, so the hydroxide is in the solution. And basically when something is acidic, why you want to maintain a pH is because if you have too many of those hydrogen ions, they're an ion, which means they have a charge and they're floating around, and that charge wants to do stuff, right? It wants to attract stuff. So we are biomolecular organisms, and our proteins work on these hydrogen bonds actually when we talk about. So having positively charged ions or negatively charged ions all of a sudden floating around near our proteins is bad because they can break those hydrogen bonds and damage our proteins and damage things in our bodies. Okay, that is it for this first section. Huge section. This is all really review, but there you go. In case you don't know it, now you do.